Okay, I'm going to do a review for the final exam. I'm not going to cover chapters 5, 6, and 7. There are plenty of videos that you can review for those chapters. I'm going to specifically focus on chapters 1, 2, 3, and 4, the ones we did when we were in class. Also, look, you have your booklets that were given to you at that time. I would definitely refer to those, but I'll give you some idea of what some of the problems are going to be on the final exam and what you need to know. On chapter 1, there's not a whole lot. One thing is sig figs we covered, and dimensional analysis. So these are probably the ones that you'd probably want to go back and take a look at, redo. There is one other problem, and it has to do with uncertainty. The other part, the last part of chapter 1 was this trig. And I don't think I'm going to ask any trig questions on the test because you'll be doing some trig for some of the other problems on the test. So we're going to leave those out. Okay, so let's talk about uncertainty. Uncertainty. This is concerning, you have a area, length times width. You have 18 meters on the length and the 15 meters on the width. And you want to know what is the uncertainty, okay? So you have a measuring device, a ruler, a scale, tape measure, and the lowest increment on this tape measure is 0.015, okay? And so we have the format of the width and the length. We have the 15 meters plus or minus 0.015 meters, and then the length, same thing, 18.015. And so what we want to do is that we want to find the uncertainty of the amount of area, not the percent in this case. We're just looking at the uncertainty. So we use this formula right here. The delta width is the 0.015 for both, and then you divided by whatever that dimension is, times the area is equal to the uncertainty of the area. So plugging the numbers in, we get 0.495 square meters. This is roughly a half a square meter. And that would be the uncertainty of using that tape measure that has those small increments, and this would be the amount that you would be off. So we did one or two of these, so go back in your notes and take a look at that. Okay, chapter 2. Chapter 2 was kinematics. In it was actually learning the study of motion, acceleration, velocity, displacement, and you were shown and taught some equations, acceleration equations, and also average velocity, constant velocity. So those are the types of equations you need to be familiar with if you're not already. So let's just take a look at what they are. Let's first start off with constant velocity. We'll define that. Constant velocity is equal to the change in displacement and divided by time. Okay, constant velocity, if it was v over t, it would look like this, a straight line, okay? For a x versus t, constant velocity would just be a diagonal line, okay? So there's no acceleration. No acceleration. What about average velocity? We talked about average velocity, where we have the final two velocities, initial, divided by 2. Okay, this is also something that comes into play when you're solving for some of the problems for solutions. this is taking the two velocities and divided by 2, you get an average. Okay, so what you have is that you have the displacement is equal to the average velocity times time. And you have v plus v synod divided by 2 times t. Okay, and so this can be two things. This can be where you have an acceleration, or if you were taking two readings of velocity at 2 points on an experiment and they both were the same, then that would tell you if v and v synod are the same, then what I have basically is constant velocity. So you have to watch out for that, because average velocity could also look like this. Okay. And therefore it would be constant velocity. The other equations that were used were v equals v synod plus the acceleration time, v squared minus v squared naught equals 2 acceleration displacement times displacement. And this one, delta x equals v synod t plus 1/2 a t squared. So with these equations, you can just about solve any problem. It's just a matter of making sure you understand the problem and using the right equation. I don't think I really need to go into this chapter any more than what I'm doing right now for a review, because you pretty much have used these equations throughout the whole semester. Okay, with that, we'll go into chapter 3. Chapter 3 covered two things: vectors and projectile motion. First, let's talk about vectors. Okay, vectors are simply like little arrows that give direction and magnitude. Okay, so if we have a coordinate system and we have a vector right here, call this vector A, okay, it has vector components. Vector A will be equal to AX plus AY. Let me rewrite that. Okay, AX and AY. And so to find, if you had information of what AX and AY is, you could find what the resultant vector, in this case A, would be equal to. But what happens if you have two vectors? And this is what we kind of worked on. If you had another vector right here, and this was vector B, okay, and you were asked to add that. Well, remember what you do when you add vectors. In this case, here is vector A, and then it's from head to tail, and so this would be right to here, okay? So this is vector B, and then the vector, the resultant vector, if you remember, would be from the center point of the first vector and to the head of the second vector. And this would be if you're adding B and A. Also remember too, if you have A is equal to A, I'm sorry, let's make this R, okay, R equals, you have A plus B, would be just the example right here, and then you could have R equals A minus B, and we don't have negative vectors, or actually we don't subtract vectors, we have negative vectors. This would be A, okay, plus minus B, okay. And so what is a negative vector, or what is it? It's an inverse vector. So in this case, we have B over here. B would be on this side right here. Okay, and then you're ready to add. Okay, So what do you do when you have two vectors? Well, if you remember, you have to find r of x and r of y, okay? So what is rx and what is ry? Okay, so the first thing is you would have your a and b vector. You'd have a, and every one of these vectors for the x would be cosine, okay? And then you would have the angle for your first vector, plus then you would have b, the magnitude of the b vector, times the cosine of its angle, and we would call that phi, just to designate the two different angles of the two different vectors. Okay, and then we do the same for y. We had a, we'd have sine theta plus b sine phi. Okay, sorry, sine phi. Okay, so this, once you found this, then you could find the magnitude of each vector by taking the sums of the square root, rx squared plus ry squared. And then you could find the angle by taking the inverse tangent of ry on top and rx equals the angle, and I'll subscript that r, of the resultant vector. So go back and take a look at vectors. They're pretty much self-explanatory. You may have on a test 3 vectors, okay? So you'll have to add 3 vectors. That just basically is that on rx and ry, you will just have another term. So if you had 3 vectors, you'd have plus c cosine some angle, let's call that alpha. That would be specific to the third vector, c, okay? And you do the same thing for y. So next thing, let's talk about projectile motion. Okay, this was the second part of chapter 3, projectile motion. And this is where you would have been given an initial velocity of something, and you would also be given an angle that this projectile was launched at, okay? And therefore you could find out the maximum time is in the air, the maximum height, and the maximum range. The maximum range is x max, and t max is the maximum time. So is there actually only 2 equations that run this whole thing, and that is for x you have the delta x, or this would be the maximum range, times v, and this v is actually should be the initial velocity, times cosine theta, wherever that angle is, times t max. And the same thing with y, except for you have a gravitational field affecting the vertical, so you have to use a different equation, and this one has g in it, and the 2 t's right here, they are t max. Okay, then you can solve for delta y. Now, in these problems where you're solving for anything, one of the first things you probably need to do, and I would say in most all cases, is to solve for t max, okay? Now, in this case, finding t max, you don't have to use the quadratic equation like you would down here off a building. You would have to use that, okay? So you can basically have this equation right here. We use this equation, but because of delta y is going to be 0. The initial y starts off as 0 on y, and it ends on y, final y of 0 too. So you have 0. So that helps out by taking this equation and making this delta y 0. In that case, we can go ahead and use algebra, and we can solve for time. We take these 2 equations, okay, and go to this, and then go to this last one right here, which is t max. Now that is only if you launch a projectile from the same level and it lands at the same level. If you are off a building, then you're going to have to go ahead and you're going to have to solve for Tmax by using a quadratic equation. Just remember that when you solve off a building, that this delta y is different now. This delta y is going to be the height of the building, and it has to be negative because what you're going to do is you're going to have your coordinate system be right there, okay? And so if the building is, say, 50 feet, okay, that's going to be a negative 50 feet or meters, whatever you use. So go back again into the book, review how to find Tmax, how to find Xmax, Ymax. You will certainly be asked a couple questions on the final exam on projectile motion, but it all comes down to these two equations right here, understanding those two. Also remember that in the horizontal you have constant velocity. That velocity is the same in that direction. The only velocity that's changing is in the vertical, and it's slowing down as it goes up. Once it reaches y max, your vertical velocity is now 0. But at y max, your horizontal velocity is still constant. You still have horizontal velocity. So keep that in mind, because if you were measuring something from the y max point, it's going to still follow the same parabolic curve, the rest of it, until it hits the ground. So a problem that you may want to take a look at, where you have a projectile hitting something in midair, and you'll need to know where in the range was that. So that would be X impact. It would happen at T impact. Okay, and then it would have a height too from there. So those, we did a experiment. You should have that information, and I would definitely review that also too. Okay, so now let's move on to chapter 4. Okay, chapter 4 was on force. Okay, and let's just go through the Newton's 3 laws of motion. The first law is about inertia, okay? And it says that all mass or all bodies want to stay at rest or in constant motion. So in other words, you'd have to have some external force acting on the body or mass. So if you have a mass that's resting, a brick or something, okay, it's going to have a normal and it's going to have the weight. Okay, so this brick right here has no external forces, so it's just at rest right here. But so this is applicable to Newton's first law. Now the second law is that it's simple. All force is equal to mass times acceleration. So once we have an acceleration on this mass, now we are using the second law. The third law has to do, for every action, there's an opposite and equal reaction. Okay, in other words, if you have, a good example is a missile or a rocket ship taking off, okay, and as it takes off, its exhaust goes in one direction and the missile itself goes in the other direction. This is an equal but opposite reaction. When it's unbalanced, the rocket will actually move forward, upward. If it is in equilibrium, then it's just standing still with the exhaust coming out but not moving any further. So this is the 3 laws. So if you remember that all forces, the net force is the summation of forces you have in the system. So whatever force you do, you have to sum those forces up. You could have forces that could be in the X or the Y, and you have to sum those up separately. So let's go on and talk about some applications. Okay, one application I want to talk about is where you have a mass on a table, and we did some of these, and you have a second mass over here. We'll call this M2, M1. This is hooked up by a pulley system. Okay, and so you want to find the acceleration. This mass here is M1, and we're going to say it's equal to 5 kilograms. M2 is equal to 10 kilograms. Okay, so how do you do this problem? Well, you want to find the acceleration. So let's take M2, and we just need to take one of these, and let's draw a free body diagram. And by the way, I didn't cover that in the last slide. A free body diagram, well, we'll do it here, but a free body diagram for M2, mass 2, would be, first of all, its weight, which is M2G, because this is mass 2. And then we have to also draw in the vertical what is the force on this side. It actually is the tension, and its tension is equal to, is coming from M1 times some type of acceleration. We don't know what that acceleration is. We want to try to find that acceleration. So if we take and use Newton's second law, we say that M1A, okay, and we're going to use this direction right here as positive. So this is negative, positive M2G. Well, what's going to happen when you let go? Well, what's going to let go is that mass 2 is going to start accelerating down. So this must be equal to mass 2 times acceleration. Okay, and that's just Newton's second law. So now all we have to do is solve for acceleration. And that is going to be M2G, the sum of M1 plus M2. Okay. Now this is the easy one, because if you have friction, then it's going to be a little different. So let's take a look at a friction. Okay, so let's just say, I'll just draw this again here. You have a pulley, you have a mass here hanging down, and you have a table. Okay, this is M2, this is M1. Okay, so you have a frictional surface. Let's just say that frictional surface is going to be mu equals 0.222. Okay, so now let's draw a free body diagram again for what's happening to M2. Okay, so M2 is going to have, again, positive down. It's going to have M2G, and then it's going to have two vectors, both tension up here. One is going to be the tension from the mass itself. That's going to be M1 acceleration. Okay, and the second one is going to be by the normal force. So let's take a look at that closer. So you have M1 right here. It has a frictional surface. So the equation is F mu normal. So this becomes friction mu mg. Okay, and of course that friction is going to be acting in this direction. Okay, so what you have is that you have first two vectors here. One is m1a and the other one is going to be mu 1g. Okay, and so you put this together the same way, the last problem, and let's do that. Minus mu m1g minus m1a plus m2g is all going to be equal to, again, what's happening to M2? The accelerating down, M2A. So this is what you get, and now you have to solve for the acceleration, okay? So let's do that. The acceleration is going to be equal to G M2 minus mu M1 divided by the sum of both masses. So the next thing, a couple other things I'm going to cover is friction and forces on a slope, and also tension, a tension problem. And that will pretty much cover chapter 4. Okay, continuing on chapter 4, you're going to have some problems with force on a slope, a mass on a slope, and let's talk about how to solve a problem. First of all, you have a slope. We can call this, we'll call this 30 degrees. Okay, and we have a mass, let's say we have a mass of 5.0 kilograms, okay? So what we want to do is that if we have this mass sitting on the slope, no friction on the slope, and we let go of it, it's going to slide down the slope. It's going to accelerate down the slope. And we can find the acceleration, and we can find the force. Now, one of the things that you need to really do is to draw a free body diagram. Okay, in this case, in the vertical, we have the normal force, and then we have the perpendicular force to the normal, to the F of parallel. And then on the slope, parallel to the slope, we would have the frictional force, and in the opposite direction, we will have the parallel force. And this direction going down is negative, going up is positive. So let's look at how to solve a problem like this. Well, first of all, we need to really just concern ourselves with the parallel force if there's no friction. So the parallel force is equal to negative mg sine 30 degrees. That is the force that will let the mass come down and travel, accelerate at a certain velocity. Now, if there was friction, then the frictional force, we'd have to add that to the net force. Now, how did we come up with mg sine 30 degrees? Well, it actually has to do with this right here, this triangle right here. Okay, so this triangle, let me just turn it around here so it looks something like this. Right here, this is mg. Okay, this is F parallel, and this is F perpendicular, okay? And so if we want to find F parallel, all we have to do is basically the sine of theta is going to be equal to F parallel and mg, which is the hypotenuse of this triangle. Okay, and so this is how we solve for F parallel. Now, of all the forces that are acting on this, if there is friction, we can say that our net force without friction is just equal to the parallel force. With friction, it's going to be equal to the parallel force and the force of friction. Okay, in this case, we would just put that there, and we'd be putting kinetic friction there. Okay, so now we just need to solve the problem. Okay, so we didn't talk about what the frictional force is equal to. Well, the frictional force is equal to the coefficient of friction, mu, times the normal force. Okay, so what is the normal force? Well, the normal force up here is actually opposite of F perpendicular. F perpendicular, put it up here, is equal to mg, negative mg, cosine 30 degrees. So if the normal is opposite, then the normal is going to be equal to mg cosine 30 degrees. So this is going to be equal to mu mg cosine of 30 degrees. Okay, so now all we have to do is to find the net force. Okay, so let's write that out. The net force is going to be equal to, first of all, we'll put the frictional force in. Okay, and here's our equation. And the net force is going to be telling us the direction and the amount of force it's going to be going. Okay, I don't have any numbers here to put in, but when you do find the net force, and this is the way to find it. Also, once you find this force, okay, so whatever this force is, let's just say that it's equal to 200 newtons, okay? You could find the acceleration down the slope by simply using the Newton's second law equation, acceleration, force divided by m. And that will tell you the acceleration going down. Then from there, if you are to want to find a velocity at a certain distance, then it's just a matter of using the kinematic equations. And you don't have to use any trig in this at all, no cosine or sine. So basically, this is how you solve it. Like I said, if there's no friction, then you would not have this right here. Okay, if we have, on tension here, we have two poles a certain distance away. Okay, and on the poles, let's just say it's a street light, and you have two cables. Okay, we are told that the first one, theta, or I'm sorry, this on this side, theta 2 is equal to 30 degrees, and on the side here, where this is theta 1, is equal to 45 degrees, okay? And so the tension, this is T1 and this is T2. And so we want to find what is the tension in T1 and T2, each cable. So the first thing you do is draw a free body diagram. So let's do that. So here we have T1, T2 in the perpendicular, and we have T1 and in the vertical, and T1 and T2 in the horizontal. Now what we can say about this is that T1 is equated to T2. This system is in equilibrium, so T1 must be equal to T2, and T1 plus T2 must be equal to mg. So we'll take the x-axis first. Okay, so what is T1? T1 is the cosine of 45 degrees is going to equal to T2, the cosine of 30 degrees. It's cosine because we're dealing in the x-axis. Okay, this works out to, let's solve for T2. And this is going to be cosine 45 degrees divided by cosine 30 degrees. And this is going to be equal to 0.817. And I'm sorry, there's also a T1 in here, times T1. So T2 is equal to 0.817 T1. Okay, that's what we found out. Now we actually have two variables, so we need two equations. So the second equation is what's happening in the vertical on the y. And this is T1 sine 45 degrees plus T2 sine 30 degrees is going to be equal to mg. Okay, and let's just say our mass is equal to 5 kilograms. All right, so now what we're going to do is that we're going to substitute T2. We're going to get rid of T2 and we're going to replace it with this. So let's rewrite that. T1 sine 45 degrees plus what T2 is equal to 0.817 T1 sine 30 degrees equals mg. Okay. So now we need to take T1 out of there. And so that would be T1 sine 45 degrees plus 0.817 sine 30 degrees is equal to mg. Now we're just going to solve for mg, for T1, I'm sorry. T1 is going to be equal to mg on top and on bottom sine 45 degrees plus 0.817 times the sine of 30 degrees. Okay. And so this gives us on top 49 newtons, actually the weight of the light, and all the in the denominator works out to be 1.12, and this comes out to 43.9 newtons. So we solve for T1, 43.9 newtons. Now let's solve for T2. Well, remember the other equation was T2 is equal to 0.817 T1. So let's do that. 0.817, 43.9 newtons, and this is equal to 35.9 newtons. Okay, that pretty much wraps up the review for chapters 1 through 4. Like I said, chapters 5, 6, and 7. There's plenty of material on YouTube videos. The final exam is going to follow very closely to the types of problems that you did throughout this course. So if you are understand those homework problems that we've been doing, you should have no problem on the final exam. Just kind of go back and review some of the problems we did, like in chapter 1, 2, and 3, and 4. Otherwise, it shouldn't be too bad. So anyways, that's the end of this review, and good luck.